Topic 2, vector spaces and subspaces. So the space Rn, so you can think of, just to get started, if I had R1, you can think of that as just the real number line. So that would just be any one real number, what I've been calling a scalar value. R2, I've been using that when I mean points in the plane. So I mean it's a point in the xy plane that I could write to say like 1, 3. And in general, you have a space called Rn, which is just the space that I can get. So if I have a vector with n components, then I can describe points in Rn. So the first, just like, so in R2, I need the first component to give me the x coordinate. And I need the second component to give me the y coordinate. If it was R3, I'd need a third component to give me the z coordinate. In Rn, it gets very difficult to visualize, but you know, R or n can often be, you know, medium size, hundreds, or it can be thousands or millions. But everything that we're doing still actually works, and sometimes it's actually easier to think about the problem, even though it's a million-dimensional space, to think about it in this column space rather than in the row space. So Rn is generally going to be the whole space. So that's everything you could possibly write down, every point you could possibly write down using n components. So R3 would just be what we think of as space. So there's no point in space that I couldn't describe if I knew where the origin was and I knew what direction the x-axis was and the y-axis. Well, with just those two, then I also know the z-axis, and I could assign any point in space, you know, 3 numbers that would describe that point. So a vector with 3 components fills up a space that we generally would call 3-dimensional space. The space R2 is just going to be the xy plane. So once I have an origin, I can describe any point in the plane by or I guess I need an origin and an x-axis, and then from that I can pick the perpendicular direction to get a y-axis. And once I have those 2 axes, then I can describe any point in the plane just with a single x-coordinate and a single y-coordinate. And those would then be all of the vectors I could draw with putting the tail at 0, 0, and then the head at that point x, y. And the 2 essential vector operations go on inside the vector space. So right now it seems kind of strange because I've just said, we have this whole space, and so every operation that I've already talked about gives, you know, if I have a vector of 3 elements or 3 components and I add it to a vector of 3 components, then I get a vector with 3 components. So it means a vector in 3-dimensional space plus a vector in 3-dimensional space has an answer that's also in 3-dimensional space. So I can add any 2 vectors in Rn, or I can multiply a vector in Rn by a scalar, and that's always going to give me a vector back that's still in Rn. So the result lies in the same vector space as the thing that I started out with, or the things that I started out with. So a subset, or a subspace of a vector space, is a set of vectors, so including the 0 vector. So 0 vector always has to be in a subspace, that satisfy 2 requirements. So if u and w are vectors in the subspace and c is any scalar value, then u plus w has to also be in the subspace, and c times w has to also be in the subspace. And so the way you want to think of this is so we live in 3-dimensional space, but you could have, say, a piece of graph paper that you could imagine is the xy plane. And so if you have 2 vectors that you draw on your piece of graph paper, and supposing you said the top of your desk had z coordinate 0, then those vectors could also be written with 3 components, but the z would always be a 0. So they're still vectors in 3-dimensional space. But if I add anything you can draw on your graph paper, if I draw any 2 vectors on that sheet of graph paper, the answer I'm always also going to be able to draw on that piece of graph paper. So that graph paper you could think of as a subspace of three-dimensional. So it's a two-dimensional subspace of three-dimensional space. And so kind of there are a few more. So any line through the origin, so for instance the x-axis, would be a subspace of three-dimensional space. Any plane through the origin, so I was using the xy plane as my example, but you could take any plane. I could take this plane and tilt it a bit. Well, I guess rotating it keeps it the same plane. Tilt it this way, tilt it that way. As long as it contains the origin, that's also going to be a subspace of three-dimensional space. Yeah?
What would be what's an example of a subspace that contains vectors that would not follow these rules?
Well, this is how I'm defining a subspace. So you can't have a subspace that doesn't define.
So what would be an example, I guess, of a region, or I guess I can't imagine an area in 2 or 3 dimensions that wouldn't meet these requirements. I guess.
I guess it's sort of the point is, so remember, I'm imagining I'm living in three-dimensional space, which isn't really that hard because I live in three-dimensional space. And I'm thinking of my piece of graph paper as a subspace. And I can make the vectors in my graph paper vectors of 3 components by just always taking the z to be 0. So a vector that wouldn't be in that subspace would be the z-axis. You know, if I took the vector 0, 0, 1, that would point directly out of my graph paper. So I can't write the z-axis as the sum of vectors that live in my graph paper. Because it would always, if I made a linear combination, it would always be something times 0 plus something times 0 in the z-coordinate. So that's kind of what you're decomposing three-dimensional space into the xy plane and the z-axis. So yeah, I guess it's not something that's easy to visualize, but what you're after.
Like W then would have to be, 0, 0, 1 and or something similar, and the z dimension doesn't exist in your subspace. So.
Right.
Maybe I'm missing the point. Maybe the point is that it's a really exhaustive and specific definition.
Well, the point is, so that's the easiest one, is the xy plane. But imagine I tilted the plane. Now you have points where everything still has to live in a plane, but you can have points in that plane that have x, y, and z all non-zero. But there's no way, because there's no vector in that subspace perpendicular to the plane, there's no way for me to get off of the plane. So that's kind of, I use the xy plane because it's an easy example. But what I want is really all possible planes that could be, that could exist in 3 dimensions that contain the origin. And I think really what we're after, because that's kind of the highest dimensional thing you can even really reasonably understand. What I'll want to be able to do later on is, these vectors will be in, say, like a 7-dimensional subspace of 10-dimensional space. So it's not something you can really visualize. But I'm just trying to give you an idea of what it means to, so you're sort of stuck in the things, like you only need, if you're in a plane, you only ever need 2 numbers to describe where you are. If you're in full 3-dimensional space, now I need 3 numbers. And so that's how it's going to show up later on. So for instance, in the xy plane, if z is always 0, then I only ever need to know x and y to know where I am in my subspace, right? So being in that subspace is giving me a constraint that allows me to get from the first 2 components of that vector. It allows me to figure out what the third one has to be. And so that's the property that's going to be useful later on. And also the whole space. So if I'm talking about 3-dimensional space, all of 3-dimensional space is also going to satisfy my definition of a subspace. and the 0 vector. So this is a particularly easy one. There's only one vector in the 0 vector subspace. So if I add it to itself, I still get 0. And if I multiply it by any number, I still get the 0 vector. So that also, it seems like kind of a strange one to have, but it's a vector that satisfies those two properties. So it's a subspace. So one subspace that's particularly useful in statistics is the column space of a matrix A. And so this ends up being all of the linear combinations I can write using the columns of A. So the way I get a linear combination of columns of a matrix is I multiply it by a vector. So this is when I want to think about what are the vectors that live in the column space of A. That's every vector I can write as A times X. So A is an M by N matrix. That means X has to be a vector with N components. And it's going to give me a linear combination then of the columns of A. And for every vector X that I pick, I can get a different output from that. And those vectors are going to fill up a space, and that's called the column space of a matrix A. Okay, so the linear combinations are things that I can write as AX. And so remember when we were looking at solving this problem AX equals B, well, this is, according to this definition of this column space, this is only going to be solvable if B is in the column space of A. So I think in the homework, and I also gave a few quick examples of, sometimes you're not able to solve AX equals B, or sometimes you end up with an infinite number of solutions. And so when you're not able to solve AX equals B, so you end up getting something like 0 times y equals 8 when you're doing your elimination, that means that for that particular case, for that particular A, the B that you're trying to solve in this equation here is not in the column space of A, so you're not going to be able to find an answer for that. So if A is an M by N matrix, then the columns of A have M components. So the columns live in a subspace, or they live in the whole space Rm. And so the column space has to be a subspace of Rm. So if N was equal to M, then it's possible that A could fill up the whole space. If there are fewer, so for instance, if you think of A as being the identity matrix, then what the identity matrix really is, the first row or the first column is 1, 0, 0. That's a vector that just points along the x-axis. It points 1 in the x direction and 0 in y direction, 0 in the z direction. The second column is 0, 1, 0, so that's a vector that points in the y direction. And the third one is a vector that points in the z direction. And so then when I take A times X, so if I take I times X, the reason that's equal to X is it's just how I would write the, the point X, Y, Z in terms of go so much in the X direction, so much in the Y direction, and so much in the Z direction. It's a linear combination of my coordinate axes. If I only had the first two columns, I could never get in the Z direction. So even though my vectors are still length 3, so I'd have 1, 0, 0, and 0, 1, 0. Now, since I only have these two vectors, I can't fill up the whole of the space anymore. I can only fill up a plane. I can only get to points in the xy plane. And then just a bit of notation. So for some reason, they call the column space the range of a matrix. So the notation is R of A. So I think R is going to get used quite often as a variable or a function here. So in this case, when I write it like this, R of a matrix, I mean the range of the matrix. And that's the subspace of vectors that I can write as linear combinations of the columns of A. So R stands for range. Okay. Then another space that's will show up as being important in statistics is called the null space of A. And this consists of all of the solutions. So here I'm looking at solutions x to the equation ax equals 0. So remember I said the 0 vector was its own subspace. So you always get that one for free. If I put in 0 for x, then I'm going to get a times 0 is equal to 0. So 0 always is in the null space. The null space of A is denoted by n of A. So we had R of A for the column space, and then n of A for the null space. And so again, remember when I was talking about using the identity matrix as my matrix A, if I took off the third column, then the points I couldn't get to are the points that are on the z-axis. So that would mean the z-axis would be the null space of that matrix, and the column space would be the xy plane. And where you're going to end up with a null space is if you have a matrix where when you do elimination, so for this case, I'm going to subtract 2 times the first row from the second row, and that's going to give me 0, 0, 2. And then I'll subtract 3 times the first row from the third row, and that's also going to give me 0, 0, 2. So when I look at this matrix here, there's no pivot for me in the second column, so I have to go to the third column to find a pivot. And then when I subtract the second row from the third row, I end up with a row that's all zeros. So I end up with pivots only in the first and third column, so I get pivot variables x1 and x3. And I'm going to call the variable x2 a free variable. And essentially what free variable means is I can pick that, and then I can solve for the other two in terms of whatever I pick there. So you can think of that as just sort of like y equals a function of x. You have a dependent variable and an independent variable. So I can choose any value I want of the independent variable, but once I've picked that, I now have a function that gives me a specific value of the dependent variable. And so if I, normally what I expect to do, what I expect to get when I have 3 equations and 3 unknowns, I expect to be able to solve that and get an answer, a single point. If I end up with, when I've done elimination, something like this, now what it's telling me is that I sort of have 0 times x2 can be 0. So that means I can choose any value I want for x2. And then I'm going to have, based on this equation here, I'll have some way of getting x1 and x3 from whatever value I choose for x2. And so I'm going to use that to define kind of one last important property of a matrix, which will be the rank of a matrix. And so the rank of a matrix is going to be the number of pivots of that matrix. And so in this case, since I have a pivot here and a pivot here, this matrix that I started out with has rank 2. If, on the other hand, if I got the nice elimination picture where I have non-zero values down the diagonal, then it would be a rank 3 matrix.
What is a null space then?
That we have to take a linear algebra class for. So it's not really clear from this exactly what the null space is, but you can see that it has, if you only have x equals 0 as the null space, that's kind of a trivial null space. It's sort of like saying anything times 0 is 0. Here, because I have this free variable, I don't have enough pivots, it means I have a non-trivial null space. It means I can actually find non-zero vectors x that are going to satisfy this equation. Okay. Then I think the final concept for this topic will be linear independence. So suppose I have a sequence of vectors, v1 up to vn, and I'm going to call that linearly independent if and only if the only linear combination that gives the 0 vector is 0 times v1 plus 0 times v2. So it's basically 0 times each one of these vectors. So that's the only way to write the 0 vector. So columns of A are independent, so linearly independent, if the solution to AX equals 0 is the 0 vector. So that's just another way of stating the same thing. So this is the vector definition of linearly independent. This is sort of the matrix definition of linearly independent. And so this is going to be true, so the columns of A are going to be linearly independent if when I do elimination on A, I don't have any free variables. So that means I have to end up with a full set of pivots as I'm doing elimination. And in that case, the rank of A is going to be equal to n. So I'm going to get a pivot in each column. And if I have a pivot in each column, there won't be any free variables. So the null space of A will contain only the 0 vector. Okay. And then I'll say a set of vectors spans a space if their linear combinations fill that space. So for instance, if I look at the identity matrix, so say 3 by 3 identity matrix, I can write any point in three-dimensional space as x times the first column of the identity matrix plus y times the second column of the identity matrix plus z times the third column of the identity matrix. So I'll say that the columns of the identity matrix span the space R3. So any point in that space can be written as a linear combination of the vectors that span that space. And then a basis for a vector space is going to be a sequence of vectors, so same thing as this. They need to be 1, linearly independent, and 2, they need to span the space. And so again, this is something like my columns of the identity matrix would solve this. They're linearly independent, and they span the space. And that's a very trivial example, but that's kind of what you're trying to say. So it's the columns of your matrix give you a way, so I can write every point in R3 as some linear combination of the columns of that matrix. And then the identity matrix is obviously just the easiest way to do that, which is why that's what everybody uses. And the dimension of a vector space is going to be the number of vectors in the basis. And so since every basis has to have the same number of vectors, we say it's the number of vectors in every basis. And so again, if I'm talking about R3, I need the columns of the 3 by 3 identity matrix to span that. That's also going to be a basis for R3. And so the dimension is just going to be the number of vectors, which is the number of columns of the 3 by 3 identity matrix, which is 3.